morning, everybody. Hope you've had a great weekend and welcome back to this session on machine learning. I just wanted to give you a quick overview of the week, this specific week, and also about the first version of project number 1. So this day today, we are going to have a slightly shorter session, so we will end at 9 o'clock because I have unfortunately to be at a meeting. But I wanted to wrap up the discussion on optimization. And at the same time, I want to link this with project number 1. So if you scroll down on the topics which we've been covering, you will see now that we have the videos from last week. And last week, we discussed optimization problems in more detail. And we looked at the different ways by which we can calculate the gradients. And this is, as we discussed last time, it's one of the true bottlenecks of machine learning. Today, we are going to wrap up these discussions, and we're going to look at project number 1 as well. And then next week, or actually it will be the week thereafter, because I have a workshop I'm running next week. So we will meet again in the week, which begins with Monday the 12th. And then we will try to use that as the last week before we go for winter break. And then we will have some new sessions in the beginning of January. Now, project number 1 is available at the link which you can uncover if you look up at the basic links which we have here under this doc folder. And if you then go into projects and click on 2022, and then again on project number 1, you will find different variants of the files. You will find an HTML variant, but you will also find a PDF variant, which also contains the basic LaTeX file. So you can actually use the LaTeX file and start writing your project based on what's laid out in the LaTeX file. But let me say something about the project before we move on. So if we take a look at it, we also have if we go to the link on the weekly plans and you scroll down, you will find project number 1 laid out here. And I put just a tentative deadline on January the 31st. And I put also a similar deadline for project number 2 on February the 15th. We can see how much time we will need. The most important thing is that we will be able to set the grades by the end of February, because this is seemingly the last deadline for punching in the grades before you start moving to doing your master thesis in different places. But if you look at the project here, oh, sorry, not project 2, but project number 1. So the project has a kind of warm-up set of data, which is called the Franke function, where we are going to apply a ridge regression and ordinary least squares to fit a function. And this is a 2-dimensional function. This is a kind of warm-up case. And we are going to discuss things like, so you will also find an example of how to set up this function and how to plot it. And then you're going to look at the ordinary least squares and going to calculate the mean square error. We're going to look at the bias variance trade-off. And we're also going to look at the cross-validation here as a resampling technique. And thereafter, we're going to deal with ridge regression, and then you can use this functionality in scikit-learn. You can decide whether you want to use scikit-learn or whether you want to write your own code for these methods. So these methods all imply just a linear algebra inversion of a matrix. Then I propose some real data where you can actually repeat much of the same exercise as you did in parts A to D. However, many of you do have your own data. So while parts 1 or A, B, C, and D are more the kind of you getting set up with the machinery, having done a cross-validation analysis, having tested ridge regression, and so on. The real data case is that perhaps the one which is more interesting. And this is where you can If you don't like the data set which I proposed there, you should feel free to propose other data sets. I also wanted to say something about the data sets. If you are looking after experimental data and you are still struggling a little bit with the type of experimental data you want to use, so suppose you have been running an experiment and the quality of experimental data is so and so, and you're a little bit uncertain whether you can use these methods applied to the data set, then one of the things you could do is to go back to the first lectures which we had. And if you then go back to the first session on Introduction on Data Analysis and Machine Learning, and also session 2 here, you have the data set on nuclear binding energies. And in the examples which we have here in session 1 and session 2, I did a very crude fit to the experimental binding energies. So this is a place where you could actually make a much better fit if you want to. So this is just another option for a data set in case the data you were promised or the experimental data you have a little bit so and so, and you find it too difficult to use that data set within the time which we have allocated, then feel free to use the data on experimental binding energies. Now, if we go back to the project itself, let me just bring it back here. So feel free to replace this data set which I propose with a data set of your own. And there are also many of you who have access to data sets. And if you want to make bigger groups where you collaborate on the same data set, feel free to do that. I mean, the most important thing is that you get a little bit acquainted with the methods and that you have a data set which you are happy with. Now, there is a final exercise here, which is optional. And this exercise is about you writing your own stochastic gradient descent code. So when we come to project number 2, I'm going to give you 2 different options. One, if you want to write your own neural network code, which we will be discussing in the week, which begins with Monday, the 12th of December. Or if you just want to use TensorFlow or other libraries, you should feel free to do that. If you write your own code for a neural network, you will find this part here very useful. So the project itself has a score of 100 points. But if you would like to do something extra and write your own gradient descent code, and in this case, I'm just proposing a simpler function, but you could take this Franke function, which I proposed in the beginning here, or you could just take just a plain second order polynomial. And then write first a plain gradient descent, then move over to a stochastic gradient descent with and without momentum. And then we have the more advanced methods, which try to include information about the gradients in the calculations of the second derivative, which is a matrix, which we have to invert if we want to use Newton-Raphson methods to calculate the gradients and find the zeros of a given function, which in our case is the derivative of the cost function. So in this particular case, this is something which essentially what this is you practicing what we've been talking about last week and the week before about optimization problems. And as I said, this is the topic today which we want to wrap up. So today there's only one topic, which is about optimization. And then we are going to wrap up the topic on optimization before we begin with neural networks. And actually being able to calculate gradients in the most possible efficient way is simply essential for all machine learning algorithms. So this is an optional point, but you can, if you want to write your own code for neural networks, you do actually need this part here. So this was a little bit about the project. Feel free to ask questions. If there are things which are unclear, you want to take a look at it. And we can always discuss this also when we meet next time. We can set aside time for discussing the project itself. So as I said, for next week, we will not have any lectures, but the week thereafter, we could have 2 sessions plus eventually exercise sessions to discuss the project. Okay, so if there are not any questions, just please take a look at the project. I'm going to send you an email with the with a reminder of the project, the deadlines, and also for the plans before we take a break between New Year's Eve and January. And then I wanted to go back a little bit to the topic this week, which is going to deal with us wrapping up the discussion on optimization, and in particular using a software which is called AutoGrad, which stands for automatic differentiation. And automatic differentiation is an extremely useful software and an algorithm which allows us to calculate gradients and derivatives to numerical precision. And it avoids also calculating the derivatives using analytical formula, where we have to derive the analytical formula, or using symbolic manipulations to actually find an expression for the derivatives. When we come to the discussion of neural networks and the so-called backpropagation algorithm, which means in just 2 weeks from now, then we are going to look at the details, the mathematical details of the automatic differentiation. So today we're just going to present the library and how you can use it. And then we are going to implement this in our discussion of the algorithms like AdaGrad, our root mean square propagation, and also on the so-called Adam algorithm. So I'm going to remind you quickly about what we were last week. So last week, we discussed stochastic gradient descent, because the standard gradient descent is a method which typically becomes extremely CPU cycle consuming, because we are running through the whole data set and calculating gradients. So one of the standard ways to avoid the time consuming part of calculating the gradient for all data points is actually to compute the gradients in so-called batches and mini batches. And the stochastic gradient descent is a method which is widely used in all these kind of optimization problems. And as we discussed last time, it's also a method which aims at allowing us to eventually calculate or finding the true local minimum or global minimum in case we would be stuck in a local minimum. Let me quickly remind you of some of the overarching things which we discussed last time. And let me now bring up the whiteboard so that we are on the same page all. So when we are calculating gradients, so when we look at the gradient calculation, gradients and optimization, so what we want is to calculate the derivative of the cost function, which is a function of different parameters beta, and we obviously want that to put that to 0. And that's going to give us the optimal parameters, which typically minimize, for instance, the mean squared error, which could be one example of a typical cost function. And the standard method which is being used is Newton's method of finding the roots of the gradient. And in that particular case, what we had is that we had an iterative process of iteration n+1, and beta is now a vector. And this contains then the beta from the previous value minus. And in principle, we should calculate this matrix, which we call the Hessian, which is the second derivative of the cost function, and it is actually represented by the Jacobian. And then we have the gradient itself. So this is a quantity which we just called g of beta. And then the gradient is calculated at the previous iteration of n. Now, this becomes extremely difficult to calculate when we have a multidimensional function to optimize. And this is normally replaced by what we call a learning rate minus a gamma as a function of n. multiply with g of beta of n. And this becomes a parameter. Now, when it comes to the calculations of this iterative process, we had two basic bottlenecks. One is the calculation of the gradients, and the other one is the calculation of the second derivative of the function we want to optimize. Now, in the calculation of the gradients, we can use standard gradient descent, which runs over all the data points, and we shorten that one to GD. And then we can use a stochastic gradient descent, which allows us to calculate the gradients in small batches, where we would place ourselves randomly in the domain of all data points which we have, hopefully then also being able to catch a global minimum, if that exists. So these methods, stochastic gradient descent, which is the kind of standard now in the literature, is the favored method for calculating the gradients, which also allows us to calculate in more optimized way the derivatives for a multivariable function. Remember now that when we are going to move to neural networks, we are going to have a function which will be truly multidimensional with hundreds of thousands of parameters we want to optimize. Then the other important topic is the calculation of the learning rate. So the learning rate becomes a parameter, and here we can have a fixed learning rate. That's the, the absolutely simplest possible approach. So this parameter gamma is normally called the learning rate. We could have an iterative learning rate. So we could have some recipe for changing the learning rate for every iteration. So we would then have a scheduler for gamma of n. And the most common ones are one which is called a linear, which we discussed last week. And we could also have an exponential decay so that the learning rate changes from iteration to iteration. These methods are what we might call a little bit more ad hoc, and they don't contain information about the second derivative or the gradients themselves. So what is common then is actually to replace these methods with what's normally called an adaptive approach. And we have in these adaptive approaches what we have then, and they contain information with info about the gradients, which then enter the calculation of the second derivative, info on g of beta of n. So the most common ones which you will encounter is one which is called ADA-grad, which we discussed last week. And then we have root mean square propagation. And one of the methods which has become a kind of standard is this adaptive method with momentum, or ADAM. So one thing you should keep in mind here is that if we now look at these methods here, there is a modification to these methods, so which is called stochastic gradient descent or gradient descent with momentum. And this is normally what is implemented, so SGD or GD with momentum. And as we discussed last week, this is the standard approach, this method here. And then the other standard approach is to use one of these adaptive methods as well. So these two main topics are those which are normally implemented in the search for the optimal parameters beta. So you would typically run with a stochastic gradient descent here with momentum. Alternatively, you would use a stochastic gradient descent with ADAM, which includes momentum, or you could run a stochastic gradient descent with momentum and an adaptive calculation of the learning rate by including information about the gradients. So ADA-grad and root mean square propagation are examples of methods where we then would use stochastic gradient descent or plain gradient descent with momentum, and then trying to find an adaptive way to optimize the learning rate. So this is a kind of bird's view of what we discussed last week. In this Jupyter notebooks or the weekly slides, you will find the code examples for implementing these methods. So if you feel tempted to include this in project number 1 as an optional exercise, feel free to look at these code examples and just implement it in your own codes. Now, there is one final topic which we need to discuss then, and this is the automatic differentiation. And we will discuss that a little bit more in detail when we come to the backpropagation algorithm for neural networks. So in automatic differentiation, this is a repeated usage of the chain rule to calculate derivatives, and it allows you to actually calculate derivatives using mathematical functions like exponentials, cosines, sines, and so on. You can calculate derivatives to numerical precision. We are coming back to this because this is an extremely important algorithm. And if you're asking me what are some of the best algorithms we have in science, I would say that automatic differentiation is actually one of these algorithms, together with, let's say, the singular value decomposition and many of the Monte Carlo methods. So automatic differentiation is the one which will allow you to calculate derivatives in an almost painless way. So you know that when you calculate derivatives, one of the standard approaches is something which is called the difference rules. So there you discretize the derivatives. So suppose you have a derivative df of x, of d of x, and if you use a centered method, so that means you need 3 points, this will be approximated with f of x plus a delta x minus an f of x minus delta x divided by 2 times delta x. You can use a simpler method which requires 2 points, and then you will get the Euler's method. And with Euler's method, you would then have an arrow which goes like delta x. With this method here, the arrow goes like O to the delta x squared. Now, this method which you see here is actually not very good for calculating higher derivatives. It leads quickly to a numerical loss of precision, because if you make delta x smaller and smaller, you will actually have round-off error, which can lead then to loss of numerical precision. So difference methods are not very useful when we want to calculate derivatives or the gradients to numerical precision. And you can actually check this one if you want to use this formula to calculate the second, third, and fourth derivative of e to the x. And with e to the x, you will see that this is going to fail miserably. The other one is what we call symbolic packages or symbolic manipulations. So where you could use something like Mathematica or MATLAB to calculate derivatives, or with Python, you could use symbolic Python. What happens often then is that the expressions you get are really written in a very impractical way for numerical calculations. So you could get an expression which depends on a higher order polynomial or some complicated functions, which normally take a lot of time to evaluate. So symbolic manipulations are normally not used. Similarly, you can calculate derivatives analytically, analytical derivations. And the analytical derivations is something which can actually take a lot of time. And also with an analytical derivation, it's easy to make errors. And it's also easy to code things wrongly. And that is why automatic differentiation is the kind of method of choice. So what I want to do now is to go back to the Jupyter notebook and take a closer look at some of the examples which you find there and how we can actually implement them in the calculations of the derivatives. So let me quickly bring this up. So last week, when we went through the examples on the stochastic gradient, and what I wanted to bring up now is actually the calculation of derivatives using automatic differentiation. So what we saw last time was the basic mathematics of methods like adaptive gradient, root mean square propagation, and Adam and other methods. But now we are going to take a closer look at automatic differentiation. So normally, we do not recommend using, let's say, numerical differentiation, the method of finite difference, as I said. They are not precise enough. And similarly, I would not recommend symbolic differentiation because you often would have to rewrite the equations in order to get efficient equations for numerical calculations. So automatic differentiation, which we will discuss a little bit more in detail when we come to neural networks and the backpropagation algorithm, because then it's important to understand a little bit better what happens, is actually an algorithm which uses repeated applications of the chain rule. And as I say here, elementary functions like the exponential, log, sine, cosine. So you can actually calculate derivatives to numerical precision. And it's actually amazing. But here we are going to simply look at how we can implement Autograd, which is a Python package, which now has been replaced by another package, which is called JAX, J-A-X. But here's a way as which you can calculate the derivative of f of x, which we know very well here. So you would simply import Autograd NumPy as NP, and then you can import the element-wise gradient of a function. And in this particular case, what I'm going to do now is simply to define the function I want to calculate the derivative of. I'm plugging in the analytical derivative. And then you see now that the only thing I need to return here is the derivative defined by this function egrad, which is included in automatic differentiation. And the package, the old package for Python, is called Autograd. And you can see now when I compare things with the analytical with the numerical derivative, you cannot see any difference between the two. So this is the derivative of the sine of x computed with the analytical expression and Autograd. So, and the difference here between what the Autograd gives you and what the analytical expression gives you is 10 to the minus 15, which means basically 0. Try to take this example and calculate the first derivative with that formula which I gave you based on centered differences, where you actually have 3 points. If you try to use that formula, you will see that the difference then will be with this case here with 1,000 points between 0 and 1, as you can see here. You will see that the difference will be something like 10 to the minus 4 to 10 to the minus 5, which is much, much worse than what you get with automatic differentiation. So there are several examples here you can play around with. So again, I'm simply calculating the derivative of this function, x cubed plus 1. And there you have the gradient here of that function. And in this case, I'm plotting this against the analytical result that I calculate for a equal to 1. So I'm putting in an argument here when I calculate my function. And if I run that one, you will then see that it returns the exact values. You can do this with more complicated functions. And if you now look at the arguments, so this is a function which depends on x1 and x2. This is highly relevant for what we are going to do with the neural networks and also with the applications of gradient methods to any other type of functions which pop up in machine learning. So you have a slightly more complicated function here, and then you calculate the derivative of this function with respect to the first argument, which is x1, and you can do that with the second argument. And in this specific case, I'm putting in values for x1 equal 1 and x2 equal to 3. I calculate the analytical expression for the first variable, the derivative, and I do the same thing for the second variable. And then I simply run the calculations and I look at the derivatives, and this is the derivative of f2 with the Autograd, and this is the analytical derivative, and you see that there is a basically a 100% match here. You can have a more complicated function using the elements of the arguments directly. So in this case, you can have x is an array of length 5, as you can see here. And then you can calculate the derivatives of this function here for different types of arguments. So you can have 2, 3, 5, 7, and then I do 22 times x to the 4th. And then calculate the derivative again, and you will see that the computed derivative is exactly the same as the analytical derivative of that same function. So it's very easy to use AutoGrad. Now, there are some cases below here. Also, you can use mathematical functions, as you can see. There's no problem in doing that. In this case, I have the square root and the exponential functions. And in that case, you can again see computed derivative are just exactly the same numbers. So I recommend strongly, when you're dealing with numerical work, to actually use AutoGrad or automatic differentiation. If you're running your codes in C++ in Fortran, you can link your Fortran or C++ code, or if you're using Julia or any other language, with the appropriate automatic differentiation libraries. And I think for C++ users, the library is called AutoDiff. So there are some more examples with loops and recursions and everything. There are some unsupported functions, which is actually not a supported item with the array box. And that's something which it doesn't like. So you would not be able to do that. So the thing which I wanted to show you is now how you can use AutoGrad with what we have done till now. So what I'm going to do now is just to show you a simple example with automatic differentiation, where I calculate just the gradient. So in this particular case, I'm just using a plain gradient descent, as we did in the very beginning of the optimization discussions. So I'm now setting up my cost function, which you can see here. So this is, instead of me setting up the gradient now, I'm just calculating the gradient of this function here, which is my cost function, the mean squared error. I set up 100 points. I define a function which is a linear polynomial in X, as you can see here, plus some random noise. I define my design matrix. I'm doing the matrix inversion to calculate the parameters using standard ordinary least squares. In this case, I also define this Hessian matrix in order to find the optimal parameters gamma. And then I just calculate my gradients. So my gradient now, this function training gradient, is defined as the gradient of my mean squared error. And in my case, the argument here is the argument beta, or as I call it here, I just call it for theta, which is the optimal parameter. And the only thing I need to do now, instead of setting up the gradient and the derivative of the function you see here, the cost function, I simply now use automatic differentiation and call the gradients, and then I simply update my function here. So it's very simple to use it, and you can see I get basically the same results here. It's not a perfect fit because I have a lot of noise in the data. If I were to take away noise here, if you look at that one, just go back here and we just take away the noise, we will get a perfect agreement with an intercept equal to 4 and a slope which is equal to 3. So if I rerun it, you will see 4 and 3, which are the exact parameters which we need. Then you can use momentum gradient descent. And remember now that momentum was the same as us using a memory in the calculation of the gradients. It means that if the gradients fluctuate a lot from iteration to iteration in the parameters beta, one of the things we can do then is to keep track of previous results on the gradient. So that means that we bring in some memory in the iterative process where we have some information about the gradient before those which we calculated. So in this particular case, if we now move on here with the calculation of the gradients, again, we use the standard definition of the gradients. So here we would have the gradients calculated in standard gradient descent without any momentum. This is this part. And what you will see then is that the method actually with momentum converges much faster than the method without momentum. And in this particular case, what we do now is that we have a parameter which we call delta momentum, which in our case defined as 3 here. And what I'm doing now is simply to include the result from the previous iteration. So in the first iteration, I put it to 0, but then change is equal to new change. So when I go back again, the new change keeps information about the results from the previous calculation. And this is a way to soften sudden increases in the gradients from one iteration to the next one. And when you run this with momentum gradient descent, this is a plane gradient descent. What you would get then is now that you run the standard gradient descent, we needed something like more than, we actually, for this specific case, we need something more than 30 iterations to actually get a gradient which is getting close to 0. Whereas if I do my momentum gradient descent, what you will see now is that I'm getting a gradient which runs much faster to 0 than the standard gradient descent. And if I take away the noise in this particular case, so let's rerun this without noise. So then we have from the own inversion, and you see now that this calculation here, we can also change the value of the learning rate. We can add more iterations. So if we do now, let's say 50 iterations, we can then see that the standard gradient descent is slowly moving to values of a gradient equal to 0. So still at 50 iterations, we do not have a gradient which is run down to 0. If I do the momentum gradient descent now, you see in this particular case that at 50 iteration, I have a gradient which is at the order of 10 to the minus 5. Now, gradient descent with momentum is the typical choice. Clearly, if you include Newton's method, where you now calculate the inverse of the Hessian matrix. So the Hessian matrix for ordinary least squares is just 2 divided by n. The design matrix transpose times the design matrix, as we have here. Then I can then simply define my gradients in terms of the inverse Hessian matrix multiplied with the gradients. If I do that, there's nothing which can compete with that. And you see that after one iteration, your gradient is practically equal to 0. And you get the same result as you get with the numerical inversion of the matrix. So the standard ordinary least squares equations. Then in the examples here, what you will find is including stochastic gradient descent with autograd, which we discussed last week without autograd. And again, you will see now that I define my cost function here. So this is just gradient descent with the autograd or adagrad method. So the first thing I do now is just to do a standard stochastic gradient descent. Now I have to be a little bit careful. So this does not include an adaptive learning rate. So my learning rate is still given by this parameter eta, which now gets updated with a linear scheduler, where we introduce some additional parameters. I have the number of epochs. I define the number of batches here, and I have a data set which now contains something like 100 data points. But I calculate now the derivatives of the cost function. As you can see here, I use now my program to calculate the gradients using automatic differentiation. But now what I'm doing is to do a stochastic gradient descent. I have a loop over the number of epochs, and I run over the batches. So for every batch, I calculated a gradient, but now I'm calculating the gradient for just a few points, where I place myself randomly in my whole data set. Then I find the X values, I find my Y values, and then I transfer these to the gradient calculation, because I have my cost function, which is just the standard mean squared error, except that I don't have the 1 over n point, because I now need to calculate this expectation value for just the points I have in the batch. And then I have a scheduler here, which is a brute force one, which allows me to update the learning rate. And then I calculate my derivatives and I perform my stochastic gradient descent. This is my own gradient descent with the calculation of the full gradient. And you see that when you do your own stochastic gradient descent, since you're doing the stochastic calculations, you don't get exactly the same values of the parameters. So for low dimensional problems like this, where we have only 2 parameters, there is actually no need to do a stochastic gradient descent. But when you go to huge data sets, when you're calculating the averages, this becomes much more efficient and much better than just using a plain method. You can do the same with a momentum gradient descent. This is the same code, just repeated now with a momentum gradient descent. And you see now that what I'm doing, I'm just including the information about the previous gradients in this quantity, which is called change. And then I have this parameter, which is called delta momentum. So this becomes an additional parameter in your fine-tuning of the data. And if you rerun this, you will then see that in this particular case, the results are, one, they're converging much quicker to the correct result. And you see that we are getting pretty close. The next thing we can do is to use adaptive gradient. So we can look at the same problem, which we had here, but instead of using this simple way of updating the learning rate, we compute now the learning rate iteration by inputting information about the gradients. And in this specific case, we are now calculating an intermediate function which simply accumulates all the gradients. And then when we do look at the update, we have the gradients times the original learning rate, eta. But now this is divided by this delta, which is just to avoid possible divisions by 0. And then I have the square root of the gradients squared. So I calculate the gradients as before, and I'm using now here, I'm actually using the automatic differentiation package to calculate the gradients without me setting up the analytical derivatives or using other software to calculate the derivatives. So I have a learning rate, which I'm playing around with here. I'm doing the standard calculation. I define the gradients here. I'm setting up the number of epochs and also the number of batches I want. And in this case, I have a slightly different function. So I have a second order polynomial, and I do 1,000 points in order to calculate my gradients. And you can see now that with ADA-grad and stochastic gradient descent, the exact result when I do the matrix inversion and calculate the optimal parameters 2, 3, and 4, we don't have any noise here, and you can see intercept equal 2, slope is equal 3, and then the term in front of the square root term, no, not the square root term, but the square term is given by 4 here. And then you see now that I'm getting pretty close. You can do the same with the root mean square propagation. This is exactly the same problem. But now I need to include a new parameter, which is called rho here, where I actually keep some information about previous results. So I'm actually going to include now an information here where I have a rho multiplied with the results from the previous iteration, plus a 1 minus rho multiplied with a new result. So this is a kind of adaptive learning rate with information about the previous gradients. And then I have the same function here where I divide by the square root of that quantity. So this is the implementation of the root mean square propagation. And you will see in this case, we're actually getting much, much closer to the exact result. And finally, there is an implementation of the adaptive search with ADA. So take a look at it, look at the equations. In this case, we have 2 more additional parameters, which are fine-tuned, and these are the kind of parameters which many practitioners recommend. And with ADA-grad and the same calculations, you will see now we are basically almost to numerical precision, spot on the correct results with a stochastic gradient descent. So these are methods which are widely used in the calculation of derivatives. At the end of the slides here, you will find an example on how to use JAX in this specific case. So JAX has in a way replaced AutoGrad, so you can still use AutoGrad, but JAX is something which is called it's AutoGrad and what's called accelerated linear algebra, and that's normally brought together for high performance numerical computing and machine learning research. And it provides useful transformations of Python and NumPy programs. It allows you to differentiate, vectorize, and parallelize. And you have what's called just-in-time compiled to GPUs and much more. So, and here's a simple example on how you would actually include JAX, and you would have to install JAX yourself on your own laptop or PCs. So this is going to conclude my session today, and I don't want to bring up a new topic, so we're not going to have a second lecture today, but I wanted to conclude the optimization part, so you see all the ingredients which are needed in order for us to be able to calculate gradients efficiently. So I've spent a little bit more time on this topic, and the reason for that is that optimization plays a central role in calculations of the optimal parameters to describe the data. So optimization together with efficient calculations of gradients is really the bottleneck in all of machine learning. And I hope I've been able to expose the basic philosophy and the basic principles and also the basic problems which you face when you want to optimize a multidimensional function. So I'm going to stop here today. I will upload the